Every night, somewhere above you, the moon hangs in the darkness. Sometimes it appears as a brilliant disk flooding the landscape with silver light. Other nights, it shows itself as a delicate crescent, thin as a fingernail clipping against the deepening twilight. On certain evenings, it vanishes entirely from view, hiding in the sun's glare while the stars reclaim their dominance over the night. This changing appearance follows a pattern so reliable that humans have structured calendars around it for thousands of years. The moon does not change its shape, of course. It remains a sphere of rock 2,159 miles across, always the same size, always the same form. What changes is our view of it from here on Earth, and understanding why this happens reveals one of the most calming truths about our place in the solar system. We are part of a clockwork universe where positions and angles create predictable patterns that repeat month after month, year after year, century after century. The moon orbits Earth at an average distance of 238,000 miles. This distance is not fixed, but varies as the moon follows an elliptical path around our planet. Despite these variations, the moon remains Earth's closest celestial neighbor, far nearer than any planet or star. Light takes just over 1 second to travel from the moon to Earth. When you look at the moon, you see it as it existed 1.3 seconds ago, a trivial delay that makes the moon feel immediate and present in a way that distant stars never can. Those distant suns show us light that left them years, decades, or millennia ago. The moon exists in what feels like our present moment. The sun provides all the light we associate with the moon. The lunar surface reflects approximately 12% of the sunlight that reaches it, giving the moon an albedo of 0.12. This makes the moon about as reflective as an asphalt road, which might surprise you if you've ever stood beneath a full moon and felt the landscape bathed in what seems like substantial illumination. Earth, by comparison, reflects about 30% of the sunlight that strikes it, giving our planet an average albedo of 0.3. If you could stand on the moon and look back at Earth, you would see our planet shining more than twice as brightly as the full moon appears from here, a brilliant blue and white gem hanging in the lunar sky. At any given moment, the sun illuminates exactly half of the moon's surface. This is true for all spherical objects in space, just as Earth always has a day side facing the sun and a night side turned away from it. The moon spins on its axis at the same rate it orbits Earth, a phenomenon called tidal locking that ensures the same hemisphere always faces our planet. This means the moon does have a far side, but it does not have a permanent dark side. Both hemispheres of the moon experience approximately 2 weeks of sunlight, followed by 2 weeks of darkness as the moon rotates. The far side receives just as much sunshine over time as the near side. The only difference is that we on Earth can never see the far side directly from our vantage point on the surface. The phases we observe result from the changing angle between the sun, moon, and Earth as the moon travels along its orbital path. When the moon lies between Earth and the sun, the hemisphere facing us remains in shadow, creating what we call a new moon. When Earth sits between the moon and sun, we see the fully illuminated hemisphere, creating a full moon. At intermediate positions, we see varying amounts of the illuminated portion, creating the crescent, quarter, and gibbous phases. The entire cycle from new moon through all phases and back to new moon requires 29.5 days on average, a period known as the synodic month. This is the lunar month that governs the cycle of phases and has influenced human timekeeping since ancient civilizations first looked up and began tracking the moon's appearance. The word month itself derives from moon, a linguistic fossil preserving humanity's long relationship with lunar cycles. Before artificial lighting, the moon's phases had profound practical importance. A full moon allowed travel and work after sunset. A new moon meant darker nights when predators held greater advantage. Agricultural societies timed planting and harvesting around lunar cycles. Religious festivals aligned with specific phases. The moon was not merely a celestial object, but a governing force in daily life. Today, we notice the moon more casually, but that ancient connection persists in our language and culture, in the names we give to full moons and the attention we still pay when a particularly bright moon hangs low over the horizon. The moon moves through the sky from west to east, in the same direction Earth rotates. You can observe this motion by noting the moon's position relative to background stars over several hours, or by checking where the moon appears on successive nights. Each night, the moon rises approximately 50 minutes later than it did the night before, a consequence of its eastward orbital motion combined with Earth's rotation. This gradual shift means the moon occupies different parts of the sky at different times during its monthly cycle. A new moon rises and sets with the sun, remaining invisible in the solar glare. A full moon rises around sunset and sets near sunrise, spending the night crossing the sky. The quarter moons rise around midday or midnight, visible in the afternoon or morning sky respectively. This predictable pattern provides a sense of cosmic order that has comforted humans throughout history. The moon does not wander randomly. It follows laws of motion and gravity that ensure it will appear in expected positions at expected times. Even without clocks or calendars, an observer can estimate the date by noting which phase the moon displays and where it appears in the sky. This reliability made the moon an essential navigational tool for travelers crossing oceans or deserts where no other landmarks existed. The moon's phases served as a calendar visible to everyone, rich and poor, educated and illiterate, connecting all humans through shared observation of the same celestial changes. Tonight, somewhere in the world, someone is watching the moon. Perhaps they're seeing a thin crescent setting in the western twilight, marking the beginning of a new lunar cycle. Perhaps they're observing a full moon rising in the east as the sun descends opposite, creating that brief moment when both luminaries share the sky. The moon you see is the same moon every human who has ever lived has seen. It is older than any human civilization, older than our species, older than complex life on Earth. It has witnessed the rise and fall of continents, the birth and death of countless species, the slow evolution of life from single cells to the vast diversity of organisms that now populate our planet. And throughout all that time, it has followed the same orbital path, displaying the same sequence of phases, governed by the same gravitational forces that shape its motion today. In the time it takes to read these words, the moon has moved approximately 10 miles along its orbit. This constant motion is imperceptible in real time, but it accumulates. Over hours, the moon's position shifts noticeably relative to the background stars. Over days, its phase transforms from one appearance to another. Over weeks, it completes an entire cycle from new to full and back to new. This journey continues whether we observe it or not, whether the sky is clear or clouded, whether we're awake or asleep. The moon orbits regardless of human attention, following a path established billions of years ago when gravitational forces shaped the Earth-Moon system into its current configuration. What follows is an exploration of these changes, a detailed look at why the moon appears different from night to night and what these appearances reveal about orbital mechanics, gravitational interactions, and the geometry of the solar system. We'll move slowly through the phases, examining each in turn, understanding not just what they look like, but why they occur, and what that tells us about the Moon's position relative to Earth and Sun. We'll explore the subtle differences between how long the Moon takes to orbit Earth relative to distant stars versus how long it takes for the phases to repeat. We'll discover how the Moon rocks slightly back and forth in its orbit, allowing us to see more than half its surface over time. We'll learn about the phenomenon of Earthshine, where our planet's reflected light illuminates the dark portion of a crescent moon. We'll examine the Moon's elliptical orbit and how variations in distance create supermoons and micromoons. We'll look back to the Moon's violent birth in a collision between Earth and another planet-sized body, and forward to its distant future as tidal forces continue to push it slowly away from Earth. This is not a journey that requires action or effort. There are no tasks to complete, no problems to solve, no urgency to move from one topic to the next. The information unfolds at a pace measured in paragraphs rather than seconds, suitable for long listening sessions where understanding develops gradually and naturally. The Moon's changes happen slowly, and so too will our exploration of them. Each phase receives its due attention. Each concept is grounded in verified scientific understanding, drawn from space agency documentation, peer-reviewed research, and established astronomical knowledge. Nothing here is speculative unless explicitly labeled as such. Everything is rooted in observation, measurement, and mathematical understanding of how celestial mechanics govern the motion of natural satellites. You might listen to this as you fall asleep, allowing the information to wash over you like a gentle tide, absorbing what interests you and letting the rest recede into background awareness. You might listen while resting, finding in these explanations a kind of meditative focus that quiets other thoughts. You might simply be curious about the Moon and want to understand its phases in greater detail than you currently possess. Whatever brought you here, what follows is offered without rush or pressure, a calm and thorough examination of one of the night sky's most familiar and fascinating objects. The Moon will continue its orbit regardless of whether we understand why its appearance changes, but understanding adds a dimension to observation. When you next see a crescent moon hanging in the twilight, you'll know precisely why it appears that way. The exact geometric relationship between Sun, Earth, and Moon that creates that particular distribution of light and shadow. When you notice the Moon rising later each night, you'll understand the orbital motion responsible for that delay. When you spot a full moon near the horizon looking unusually large, you'll recognize both the optical illusion at work and the genuine variation in distance that sometimes brings the Moon closer to Earth than average. Knowledge doesn't diminish the beauty of these phenomena. If anything, it enriches observation, adding layers of meaning to something that might otherwise be merely pretty to look at. So, settle in for this exploration. There's no rush to reach the end. The Moon has been orbiting Earth for more than 4 billion years. It will continue orbiting long after you've finished listening to this. The phases will keep cycling, the orbit will keep bringing the Moon closer and farther, the tidal forces will keep slowly pushing it away from Earth. All of this happens on timescales that dwarf human experience, creating a sense of permanence and stability, even though nothing in the universe is truly static. The Moon represents change that is slow enough to feel eternal, motion that is predictable enough to provide comfort, complexity that is understandable enough to be satisfying. And it all begins with a simple observation. The Moon looks different from night to night. Let's understand why. Stand outside on a clear night when the moon is visible and you'll see a shape in the sky. Perhaps a perfect circle, perhaps a half disk, perhaps a delicate arc of light. This shape results from the most fundamental fact about the moon's phases. They are not caused by Earth's shadow falling on the moon. This is a common misconception. Lunar phases have nothing to do with Earth blocking sunlight from reaching the moon. Instead, phases arise from the simple geometric relationship between the positions of the Sun, Moon, and Earth, and how much of the moon's illuminated hemisphere we can see from our vantage point on Earth's surface. The Sun occupies a fixed position in this relationship, at least over the time scale of a lunar month. Yes, Earth orbits the Sun, completing 1 revolution per year, but during the 29.5 days it takes the moon to cycle through its phases, the Sun's position relative to Earth changes by only about 30 degrees along the ecliptic. For purposes of understanding phases, we can treat the Sun as effectively stationary, sending parallel rays of light toward the Earth-Moon system from one direction. These rays always illuminate half of any spherical object they strike, just as a flashlight in a dark room will illuminate half of a ball, no matter which way you rotate the ball. The Sun illuminates half the moon constantly. It also illuminates half of Earth constantly. The day-night cycle on Earth results from our planet's rotation, carrying us from the illuminated hemisphere into shadow and back again every 24 hours. The moon rotates too, but much more slowly. It takes the moon approximately 27.3 days to complete one rotation on its axis. By coincidence, or rather by the outcome of tidal forces over billions of years, this is exactly the same amount of time it takes the moon to complete one orbit around Earth. This synchronization means the moon always shows the same face to Earth. We see the same craters, the same Maria, the same bright highlands month after month, year after year. The far side of the moon remains perpetually turned away from our view, though spacecraft have photographed it extensively since the first Soviet lunar mission imaged it in 1959. This tidal locking does not create the phases. Even if the moon rotated faster or slower, we would still observe phases. What creates phases is the moon's orbital motion around Earth combined with the constant illumination from the Sun. Imagine the moon at different positions in its orbit. When the moon sits between Earth and the Sun, the illuminated half faces toward the Sun and away from Earth. We see only the shadowed hemisphere. This creates the new moon. As the moon continues moving around Earth, more of the illuminated hemisphere becomes visible from our perspective. We begin to see a crescent, a thin arc of light along the edge nearest the Sun. This crescent grows thicker night by night as the moon's orbital motion changes the angle between Sun, Moon, and Earth. After approximately 7 days, the moon has traveled 1/4 of the way around Earth. From our perspective, we now see exactly half of the illuminated hemisphere, the right half if you're in the northern hemisphere observing after sunset, or the left half if you're in the southern hemisphere. This is called first quarter, a term that confuses many people because it looks like half a moon, not a quarter. The name refers to the moon's position in its orbit, not the amount of illumination we see. The moon has completed 1/4 of its journey around Earth. At this point, the angle between the Sun, Earth, and Moon forms a right angle of 90 degrees. The moon continues its eastward journey, and the illuminated portion we see grows larger still. This phase is called gibbous, from the Latin word for hump or hunchback, describing the convex shape that is more than half illuminated but less than full. The waxing gibbous moon rises in the east during the afternoon and remains visible into the night, setting after midnight. Eventually, after approximately 2 weeks, the moon reaches the opposite side of Earth from the sun. Now the entire illuminated hemisphere faces toward Earth. We see a full moon, a complete disk of light rising in the east as the sun sets in the west. This is the only time during the month when the sun, Earth, and moon form a line, with Earth in the middle. You might expect Earth's shadow to fall on the moon during every full moon, creating a lunar eclipse each month. The reason this doesn't happen is that the moon's orbit is tilted about 5 degrees relative to Earth's orbit around the sun. This 5-degree inclination means the moon usually passes above or below Earth's shadow at full moon. Only when the moon crosses the plane of Earth's orbit at the same time it reaches full phase does a lunar eclipse occur, and these alignments happen only about 2 or 3 times per year. After the full moon, the moon continues moving eastward in its orbit, and the illuminated portion we see begins to shrink. This is the waning phase. The gibbous moon persists for several more nights, but now decreasing rather than growing. Eventually, approximately 22 days after the new moon, the moon reaches third quarter, also called last quarter. Once again, we see exactly half the illuminated disk, but now it's the left half in the northern hemisphere evening sky or the right half in the southern hemisphere. The moon has traveled 3/4 of the way through its orbit. From here, the visible illumination continues to decrease, forming a waning crescent that grows thinner each night until the moon returns to new phase and the cycle begins again. The entire pattern unfolds with mathematical precision. The moon moves approximately 13.2 degrees eastward along its orbit each day. Since the celestial sphere appears to rotate 360 degrees in 24 hours, or 1 degree every 4 minutes, the moon's 13-degree daily motion means it crosses the meridian, the imaginary north-south line through the zenith, about 53 minutes later each day. This creates the familiar pattern of moonrise occurring later each night. If the moon rises at 6 in the evening today, it will rise near 7 tomorrow evening and near 8 the following evening. Over the course of a month, this delay accumulates to roughly 29.5 days, bringing us back to the same phase and the same rise time. These changes are not chaotic or random. They follow from Newton's laws of motion and gravity. The moon moves in its orbit because gravity pulls it toward Earth, while its sideways motion creates centrifugal force that keeps it from falling inward. The balance between these forces maintains a stable orbit that has persisted for billions of years with only gradual changes over time. The phases follow from this orbital motion as surely as a shadow follows from a light source. Understanding the geometry makes the pattern inevitable rather than mysterious. When you see a crescent moon in the evening twilight, you can visualize where the sun sits just below the western horizon. The moon lies between you and the sun, showing only a small sliver of its illuminated hemisphere. When you see a gibbous moon rising in the east after sunset, you know the sun has set opposite in the west, and the moon is approaching its full phase when it will be directly opposite the sun in the sky. When you see a first quarter moon high in the southern sky at sunset, you understand that the moon, sun, and earth form a right angle, with you standing at the corner where the lines meet. Each phase is a clue to the moon's position, and understanding the phases transforms casual observation into 3-dimensional visualization of the solar system's geometry. The phases are not something that happens to the moon. They are something that happens to our view of the moon. The moon itself remains unchanged throughout the cycle, always the same size, always the same shape, always half illuminated by the sun. What changes is our perspective as the moon orbits Earth and as Earth rotates beneath the passing sky. The phases are a gift of geometry, a natural consequence of living on a planet with a large satellite orbiting close enough to show a disk rather than a mere point of light, and far enough to complete its orbit in a conveniently observable time span of a month. Moons orbiting other planets display phases too, but most are too small or too distant for us to observe those phases without telescopes. Earth's moon is large enough, and close enough that its phases are obvious to the unaided eye, making them one of the most accessible demonstrations of orbital mechanics available to any observer willing to simply look up at the night sky and watch how the moon changes from night to night. Astronomers divide the moon's monthly cycle into 8 distinct phases, 4 primary and 4 intermediate. The primary phases are new moon, first quarter, full moon, and third quarter. These occur at specific instants in time when the Sun-Earth-Moon geometry reaches particular angular relationships. The intermediate phases are the crescents and gibbous moons, which persist for several days between the primary phases. Let's examine each phase in turn, understanding what it looks like when it occurs in the lunar cycle and where you can find it in the sky. New moon represents the beginning of the lunar month. At this moment, the moon lies almost directly between Earth and the Sun. The precise alignment is rarely perfect due to the moon's orbital inclination, but the moon sits in the same general direction as the Sun from Earth's perspective. The hemisphere facing Earth remains completely in shadow. No portion of the illuminated side is visible. The new moon rises and sets with the Sun, spending the daylight hours crossing the sky while lost in solar glare. You cannot see a new moon with the unaided eye because it appears too close to the Sun's overwhelming brilliance. The only exception occurs during a solar eclipse, which can only happen at new moon. When the moon passes directly between Earth and Sun, aligning along the line connecting their centers, the moon's shadow falls on Earth's surface. Observers within that shadow see the Sun's disk partially or completely covered by the lunar disk. This allows the new moon to become briefly visible as a dark silhouette against the Sun's photosphere. Solar eclipses are relatively rare events at any given location because they require precise alignment and because the moon's shadow covers only a small portion of Earth's surface during any particular eclipse. For most purposes, new moon is an invisible phase, marking a transition point between the end of one cycle and the beginning of the next. Ancient calendars often started the month at the first visible crescent following new moon rather than at the new moon itself, since you cannot observe an invisible event. Islamic calendars still follow this tradition, beginning each month when observers sight the thin crescent after sunset, which can vary by a day or two depending on atmospheric conditions and the observer's location. Waxing crescent follows new moon. Waxing means growing, and crescent describes the thin arc of light that becomes visible 1 or 2 days after new moon. The crescent appears in the western sky just after sunset, hanging above the horizon where the sun recently set. The illuminated portion forms a curved line along the edge of the lunar disk nearest to the sun, while the rest of the moon remains in shadow. Depending on atmospheric conditions and the moon's exact position, you might also notice the dark portion of the moon glowing faintly. This is Earthshine, which we'll explore in detail later. For now, it's enough to know that the dark portion isn't completely invisible, but shows a subtle luminescence from sunlight reflected off Earth's oceans and clouds, then reflected again from the lunar surface back to our eyes. The waxing crescent grows thicker each night. On the evening following new moon, you might see only a delicate sliver, perhaps 5% illuminated. 2 nights later, perhaps 10%. 3 nights later, 15%. The exact percentage varies because the Moon's orbit is elliptical, causing its orbital speed to vary. When the Moon moves faster, the phase changes more quickly. When it moves slower, phase changes take slightly longer. But the general pattern holds. The crescent fattens night by night as more of the illuminated hemisphere becomes visible. The crescent also appears higher in the sky and sets later each night. On the first evening after new moon, it may appear very low on the horizon, setting soon after the sun. A few nights later, it hangs noticeably higher and remains visible for an hour or two after sunset. This combination of growing illumination and increasing altitude makes the waxing crescent a rewarding phase to observe, showing obvious changes from night to night that demonstrate the Moon's orbital motion. First quarter arrives approximately 1 week after new moon. At this moment, the Moon has traveled 90 degrees around its orbit from the new moon position. From Earth's perspective, the Sun-Earth-Moon angle measures exactly 90 degrees, with Earth at the vertex. We see precisely half the illuminated hemisphere, creating what looks like a half moon in the sky. The term quarter refers to the Moon's position in its orbit, not the amount of the Moon we see illuminated. The Moon has completed 1/4 of its monthly journey. First quarter moon rises around noon and sets around midnight. It reaches its highest point in the sky around sunset when it appears in the southern sky for Northern Hemisphere observers, or the northern sky for Southern Hemisphere observers. The illuminated half is the western half of the Moon from the observer's perspective in the Northern Hemisphere, or the eastern half from the Southern Hemisphere perspective. The terminator, the line dividing day from night on the Moon, runs approximately north-south across the lunar disk, creating a straight boundary between light and shadow. The first quarter moon is excellent for telescopic observation because the terminator crosses many interesting lunar features, creating dramatic shadows that reveal craters, mountains, and valleys in sharp relief. When the Moon is full, shadows nearly vanish and the surface appears flat and washed out. But at quarter phases, the low angle of sunlight creates long shadows that accentuate topography, making even modest telescopes reveal impressive detail. Waxing gibbous follows first quarter. Gibbous comes from Latin, meaning hunched or humped, describing the bulging shape of a moon more than half illuminated but not yet full. The waxing gibbous phase lasts about 6 or 7 days as the Moon travels from 90 degrees to 180 degrees around its orbit. Each night shows more illumination, growing from 50% at first quarter toward 100% at full moon. The waxing gibbous moon rises during the afternoon, anywhere from mid-afternoon to late afternoon, depending on how close it is to full phase. It remains visible throughout the evening and into the early morning hours, setting before sunrise. This makes it a prominent feature of the evening sky, often the brightest object visible after the sun has set. The terminator continues crossing the lunar surface, moving from the center of the disk toward the eastern limb, revealing new craters and maria in the changing light. Full moon occurs when the Moon lies directly opposite the sun in the sky, with Earth between them. The entire Earth-facing hemisphere is illuminated. We see a complete circular disk, bright enough to cast shadows and to suppress all but the brightest stars in the surrounding sky. The full moon rises at sunset and sets at sunrise, spending the entire night above the horizon for observers at mid-latitudes. Near the poles, where the sun may not set during summer or not rise during winter, the full moon's behavior differs, sometimes remaining above or below the horizon for extended periods. The full moon reaches its highest point in the sky around midnight. In Northern Hemisphere summer, when the sun rides high, the full moon appears relatively low in the southern sky. In Northern Hemisphere winter, When the sun remains low, the full moon arcs high overhead, reversing the summer pattern. This seasonal variation occurs because the full moon occupies the opposite side of the sky from the sun, so when one rides high, the other stays low. Full moons have received special names in many cultures, usually related to seasonal events or natural phenomena occurring at that time of year. The harvest moon is the full moon nearest the autumnal equinox. The hunter's moon follows the harvest moon. The wolf moon occurs in January. The strawberry moon in June. These traditional names vary by culture and region, but they reflect the importance of the full moon as a marker of seasonal time before artificial calendars became universal. Waning gibbous begins after full moon, as the illuminated portion we see starts to decrease. Waning means shrinking, though the moon itself doesn't change size. Only our view of the illuminated portion diminishes. The waning gibbous moon rises during the evening, anywhere from early evening to late evening, depending on how soon after full moon you observe. It remains visible throughout the night and into the morning hours, setting during late morning or early afternoon. The terminator now crosses from the western limb toward the center of the disk, moving in the opposite direction from the waxing phases. The moon still appears mostly full for the first few nights after full phase, and casual observers might not notice the slight flattening along one edge. But within a few days, the gibbous shape becomes obvious, with a noticeable portion of the disk lying in shadow. Third quarter, also called last quarter, arrives approximately 3 weeks after new moon or 1 week after full moon. Once again, the moon has reached a position 90 degrees from the line between Earth and Sun, but now the moon trails behind Earth in the orbital dance rather than leading ahead of it. We see the opposite half of the lunar disk illuminated compared to first quarter. The moon rises around midnight and sets around noon, reaching its highest point in the sky near sunrise. This makes third quarter moon a morning object, visible in the southern sky as the sun rises in the east. The third quarter moon shows the same terminator characteristics as first quarter, with dramatic shadows revealing lunar topography. But because it appears in the morning sky rather than the evening, many people see it less frequently than first quarter. Not everyone is up and outside looking at the sky before sunrise, whereas most people see the evening sky regularly. Waning crescent is the final phase before the cycle returns to new moon. The illuminated portion shrinks to a thin arc along the edge of the lunar disk nearest the sun, which now lies to the east since the moon is approaching its position between Earth and Sun. The waning crescent rises during the early morning hours, a few hours before sunrise, and remains visible until the sun's glare overwhelms it. Like the waxing crescent, the waning crescent can display earthshine, with the dark portion of the moon glowing softly from reflected light off Earth. The waning crescent shrinks night by night, or rather, morning by morning, as the moon approaches new phase. On the final morning before new moon, only the thinnest sliver remains visible, perhaps 5% illuminated, hanging low above the eastern horizon just before dawn. Then the moon enters new phase and the cycle begins again, starting with the next waxing crescent appearing in the western sky after sunset. These 8 phases unfold in invariable sequence, each following the previous as naturally as one season follows another. The cycle never reverses. The moon never decides to wane during waxing phase or to skip from crescent to gibbous. The geometry of the 3-body system, Sun, Earth, Moon, creates phases that must occur in this order at these approximate intervals, governed by the moon's orbital period and the constant illumination from the sun. Understanding each phase individually helps build a mental model of the moon's monthly journey, transforming the sky from a confusing display of changing shapes into a comprehensible demonstration of orbital mechanics that anyone can observe and verify simply by watching the Moon over the course of a month. The Moon's orbit around Earth can be measured in two different ways, creating two different kinds of months with two different lengths. This distinction reveals something important about how orbital motion works in a system where both objects, Earth and Moon, are also orbiting a third object, the Sun. The difference between these 2 months is subtle but significant, and understanding it clarifies why the phase cycle takes slightly longer than the orbital period. The sidereal month measures how long the Moon takes to complete one full orbit around Earth relative to the background stars. Imagine marking the Moon's position against the pattern of stars one night, noting which constellation it appears near. The sidereal month is the time required for the Moon to return to that same position relative to those same stars. This period lasts 27.321661 days, or 27 days, 7 hours, 43 minutes, and 11.6 seconds. This is the true orbital period of the Moon, the time it takes to travel 360 degrees around Earth and return to its starting position in space. The synodic month measures how long it takes for the Moon to return to the same phase. It's the period from new moon to new moon, or from full moon to full moon, or from any phase back to that same phase. This period lasts 29.530589 days, or 29 days, 12 hours, 44 minutes, and 2.8 seconds. This is the lunar month that governs the calendar and the cycle of phases, the month that people notice when they observe the Moon changing shape over time. The synodic month is longer than the sidereal month by approximately 2.2 days. Why does this difference exist? The explanation lies in Earth's orbital motion around the Sun. During the 27.3 days that the Moon takes to orbit Earth once relative to the stars, Earth itself has moved about 27 degrees along its own orbit around the Sun. This means the Sun appears to have shifted position against the background stars by 27 degrees from Earth's perspective. For the Moon to return to the same phase, to achieve the same Sun-Earth-Moon geometric alignment, it must travel slightly more than 360 degrees around Earth. It must catch up to account for Earth's motion during that time. Picture this from above the solar system, looking down on Earth's North Pole. The Moon orbits Earth counterclockwise, the same direction Earth orbits the Sun. Start at new moon with the Moon positioned between Earth and the Sun. 27.3 days later, the Moon has completed one full orbit and returned to the same position relative to the background stars. But Earth has moved about 27 degrees around the Sun during that time, so the Sun-Earth-Moon alignment has changed. The Moon is no longer between Earth and Sun. Instead, it's positioned about 27 degrees behind where it needs to be to create new Moon. The Moon must continue orbiting for approximately 2.2 more days to catch up and restore the new Moon geometry. This extra distance amounts to about 27 degrees of arc, which at the Moon's average orbital speed of 3,683 kilometers per hour takes approximately 53 hours to cover. The exact amount varies because Earth's orbital speed around the Sun changes, faster when Earth is closer to the Sun in January, slower when Earth is farther from the Sun in July, and because the Moon's orbital speed varies as its distance from Earth changes. But on average, the synodic month exceeds the sidereal month by 2.2 days, making the phase cycle longer than the orbital period. This relationship holds for any satellite orbiting a planet that is itself orbiting a star. Mars's moons. Phobos and Deimos display the same pattern. though their sidereal and synodic months differ by smaller amounts because Mars orbits the Sun much more slowly than Earth does. Jupiter's moons show the effect too, though again the differences are smaller because Jupiter's orbital motion is more gradual. The principle is universal. Measuring orbital period relative to distant stars gives one answer, while measuring it relative to the parent star gives a different, longer answer because of the parent planet's motion. For practical purposes, most people care about the synodic month because it governs the phases. If you're planning to observe the moon or timing activities around lunar illumination, the 29.5-day synodic month matters more than the 27.3-day sidereal month. But astronomers and physicists care about the sidereal month because it represents the true orbital period, the fundamental characteristic of the moon's motion through space. Both measurements are correct. They simply measure different things. The ancient Babylonians recognized this difference more than 2,000 years ago. They kept careful records of lunar positions and discovered that 19 solar years contain almost exactly 235 synodic months. This period, called the Metonic cycle after the Greek astronomer Meton, who popularized it in Athens around 430 BCE, allowed ancient astronomers to predict when lunar phases would recur on the same solar calendar dates. The Metonic cycle formed the basis for lunar solar calendars that attempted to reconcile the moon's phases with the sun's seasonal cycle, a challenge that arises precisely because the synodic month has no simple relationship to the solar year. 12 synodic months equal 354.4 days, about 11 days short of a solar year. 13 synodic months equal 383.9 days, about 19 days more than a solar year. No whole number of synodic months fits evenly into a solar year, creating the calendar problems that have occupied mathematicians and astronomers for millennia. The sidereal and synodic months also differ from yet a third lunar month, the anomalistic month, which measures the time between successive perigees, the points where the moon comes closest to Earth in its elliptical orbit. The anomalistic month lasts 27.55455 days, slightly longer than the sidereal month. This happens because the moon's elliptical orbit precesses, meaning the orientation of the ellipse, slowly rotates over time. The point of closest approach rotates in the same direction the moon orbits, so the moon must travel slightly more than 360 degrees to return to perigee. This precession results from gravitational perturbations, primarily the sun's pull on the moon, which creates subtle torques that shift the orbit's orientation over time. There's also a draconic month, measuring 27.21222 days, which tracks the time between the moon's successive passages through the same node, the point where the moon's orbit crosses the plane of Earth's orbit around the sun. The draconic month is important for eclipse prediction because eclipses can only occur when the moon passes through a node while also at new or full phase. The slight difference between the draconic month and the synodic month explains why eclipses don't happen every month. Most months, the moon reaches new or full phase while displaced above or below the ecliptic plane, so Earth's shadow misses the moon at full phase and the moon's shadow misses Earth at new phase. Only when the cycles align do eclipses occur. These various lunar months, sidereal, synodic, anomalistic, draconic, all track real aspects of the moon's motion and position. None is more correct than the others. They simply measure different things: position relative to stars, phase relative to the sun, distance from Earth, position relative to the orbital plane. Together, they create a complex pattern that early astronomers struggled to untangle, but that modern orbital mechanics explains through the interplay of gravitational forces, orbital geometry, and reference frames. When you watch the moon over the course of a month, you're observing the synodic period, the 29.5-day cycle that brings the moon from one new phase to the next. But underlying that visible cycle is the slightly shorter sidereal period, the moon's true orbital motion through space. The difference between them, those extra 2.2 days, represents Earth's progress along its own orbit, a reminder that we live in a solar system where all the pieces are moving, and where measuring one object's motion requires choosing which other object or background we measure against. The moon orbits Earth, but Earth orbits the Sun, and the Sun orbits the galactic center, and the galaxy moves through the local cluster, and the cluster participates in larger-scale motions. Motion is always relative. The moon's 2 months simply make that relativity obvious, accessible to anyone willing to observe the sky carefully and think about what the changing phases reveal about the geometry of our neighborhood in space. The moon always shows the same face toward Earth. The familiar pattern of dark Maria and bright highlands never changes. The prominent crater Tycho, with its bright rays extending across hundreds of kilometers of lunar surface, always appears in the southern uplands. The Sea of Tranquility, where Apollo 11 landed in 1969, always occupies the same position on the lunar disk. The Sea of Crises hugs the eastern limb. The ocean of storms sprawls across the western hemisphere. These features never shift or rotate out of view because the moon's rotation is synchronized with its orbit, a condition called tidal locking. Tidal locking means the moon rotates once on its axis in exactly the same time it takes to orbit Earth once. Both periods equal 27.321661 days. This synchronization is not coincidence, but the inevitable result of tidal forces acting over billions of years. When the moon first formed, it likely rotated much faster. Ancient evidence suggests the moon may have completed a rotation in as little as 5 or 6 hours during its early history. But gravitational interactions between Earth and Moon gradually slowed the Moon's rotation until it matched the orbital period, creating the locked configuration we observe today. Here's how tidal locking develops. Earth's gravity pulls on the Moon, and because gravity weakens with distance, the near side of the Moon experiences slightly stronger gravitational pull than the far side. This difference, called a tidal force, stretches the Moon slightly along the Earth-Moon axis. The Moon develops a tidal bulge, an elongation that makes it slightly ellipsoidal rather than perfectly spherical. If the Moon rotates, this bulge tries to rotate with it, but Earth's gravity pulls on the bulge, creating torque that acts to slow the rotation. Over millions and billions of years, this torque gradually reduced the Moon's rotation rate. Eventually, the rotation slowed enough that the tidal bulge became fixed, always pointing toward Earth. At this point, the Moon rotates at exactly the rate it orbits, so the same hemisphere perpetually faces Earth. This is the lowest energy configuration for the system. Any rotation faster than orbital rate would require energy to maintain the bulge, pointing in a different direction than the gravitational force prefers. Tidal friction dissipates that excess energy as heat, gradually slowing the rotation until lock is achieved. Tidal locking is common in the solar system. Most large moons are tidally locked to their planets. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, all show the same face to Jupiter. Saturn's large moon Titan is tidally locked. Even Pluto and its large moon Charon are mutually tidally locked, meaning each always shows the same face to the other, a configuration unique among major objects in our solar system. The smaller the Moon and the closer it orbits, the faster tidal locking occurs. Phobos, orbiting close to Mars, locked quickly. Distant irregular satellites may not be tidally locked because the timescale for locking exceeds the age of the solar system. The same tidal forces that locked the Moon's rotation to its orbit also affect Earth. The Moon raises tides in Earth's oceans, creating two bulges of water, one on the side facing the Moon, pulled by the Moon's gravity, and one on the opposite side, where water experiences weaker gravitational pull than Earth's solid body. As Earth rotates beneath these bulges, friction between moving water and the ocean floor dissipates energy. This tidal friction very gradually slows Earth's rotation, making days longer over geological time. 400 million years ago, during the Devonian period, Earth's day lasted approximately 22 hours. The difference came from faster rotation. Ancient corals laid down daily growth rings, and paleontologists can count these rings to determine how many days were in a year at the time the coral lived. Devonian corals show about 400 days per year, implying shorter days since the year's length is governed by Earth's orbital period around the Sun, which remains essentially constant. Each day was about 22 hours long. Over the next 400 million years, tidal friction from the Moon slowed Earth's rotation by about 2 hours, giving us our current 24-hour day. This process continues. Earth's rotation slows by approximately 1.7 milliseconds per century. That seems trivially small, but it accumulates. In 100 million years, Earth's day will lengthen by about half an hour. In a billion years, days might last 30 hours. The Moon causes this by raising tides that dissipate Earth's rotational energy. By conservation of angular momentum, the energy and angular momentum lost from Earth's rotation must go somewhere. They transfer to the Moon's orbit. As Earth's rotation slows, the Moon spirals outward, receding from Earth at a rate of 3.78 centimeters per year. This has been measured directly using laser ranging experiments. Apollo astronauts left retroreflectors on the lunar surface, small arrays of corner-cube prisms that reflect laser beams back toward their source. Observatories on Earth fire laser pulses at these retroreflectors and measure how long the light takes to make the round trip. By tracking this distance over decades, scientists have confirmed the Moon recedes at the predicted rate. 3.78 centimeters per year means the Moon withdraws about 380 kilometers per million years. When the Moon formed 4.5 billion years ago, it orbited much closer to Earth, perhaps 20,000 kilometers distant compared to the current average of 384,000 kilometers. The Moon has been moving away from Earth throughout its existence, gradually increasing its orbital period and the length of the month. This recession will continue into the distant future until Earth's rotation slows enough to become tidally locked to the Moon. At that point, Earth will rotate once per orbit of the Moon, just as the Moon currently rotates once per orbit of Earth. The same side of Earth will always face the Moon. From the Moon's perspective, Earth will hang motionless in the lunar sky, neither rising nor setting, always showing the same hemisphere. This mutual tidal locking will occur when Earth's day lengthens to equal approximately 47 current days, and the Moon's orbital period extends to match. The Moon will orbit much farther from Earth than it does now, taking longer to complete each orbit. This locked configuration represents another low-energy state for the Earth-Moon system. Once achieved, no further tidal evolution will occur because both bodies will already have their tidal bulges aligned with each other. The gravitational torques that currently transfer angular momentum from Earth's rotation to the Moon's orbit will cease. The system will be stable barring external perturbations. However, this endpoint lies billions of years in the future and may never be reached before the Sun enters its red giant phase and disrupts the entire inner solar system. The timescale for Earth to tidally lock to the Moon exceeds the remaining lifespan of the Sun as a main sequence star. So while mutual tidal locking represents where the system is heading, it may be a destination never actually reached. For now, the Moon remains locked to Earth while Earth continues its slow rotational deceleration. The Moon shows us the same face month after month, year after year. The far side remains hidden from direct view, though not because it's always dark. The far side experiences the same cycle of day and night as the near side, receiving approximately 2 weeks of continuous sunlight, followed by 2 weeks of darkness as the Moon rotates. When we see new moon, the near side entirely in shadow, the far side is fully illuminated by the sun. When we see full moon, the far side lies in darkness. The phases are reversed between the two hemispheres, a direct consequence of the Moon's synchronous rotation. Tidal locking also means the Moon's rotation appears smooth and steady when viewed from Earth. There are no visible effects of rotation because the rotation exactly matches the orbital motion. If you could somehow mark a point on the lunar surface and watch it over hours or days, it would remain in the same position on the disk, moving only with libration, which we'll discuss later. The Moon presents a face of stillness and constancy, rotating in perfect synchrony with its orbit, locked by gravity into an eternal dance where the same partners always face each other as they circle. Look at a thin crescent moon during twilight, and you might notice something subtle. The dark portion of the Moon, the part not directly illuminated by the sun, often shows a faint glow. You can make out the full circle of the lunar disk, not just the bright crescent. The shadowed region emits a soft, ghostly light, sometimes called the old moon in the new moon's arms in older literature. This phenomenon is earthshine, and it reveals something beautiful about how light travels through the solar system. Earthshine is sunlight that has made a double journey. First, sunlight travels from the sun to Earth, where it strikes our planet's clouds, oceans, ice caps, and land surfaces. Approximately 30% of this light reflects back into space. Some of these reflected rays travel toward the Moon, crossing the 384,000-kilometer gulf between Earth and its satellite. When these rays strike the lunar surface, about 12% reflect again, this time back toward Earth. This twice-reflected sunlight is what we perceive as earthshine, allowing us to see the dark portion of a crescent or gibbous moon. Earthshine is brightest when the Moon is a thin crescent, because that's when Earth appears nearly full, as seen from the Moon. Remember that Moon phases and Earth phases are inversely related from each body's perspective. When observers on Earth see a crescent moon, observers on the Moon see a nearly full Earth. Since Earth has much higher albedo than the Moon, 0.3 versus 0.12, and since Earth's disk appears almost 4 times wider than the Moon does from Earth, the full Earth shines about 50 times brighter in the lunar sky than the full Moon shines in our sky. This intense Earthshine illuminates the lunar landscape powerfully enough to allow astronauts on the Moon to navigate by Earthlight during lunar night. From our perspective on Earth, we see the result of this illumination as a faint glow on the dark part of the Moon. The amount of Earthshine we observe varies depending on several factors. Cloud cover over Earth affects how much sunlight reflects toward the Moon. When large cloud systems cover significant portions of the Earth facing the Moon, Earthshine brightens because clouds have higher albedo than ocean or land. Snow and ice have even higher albedo, so Earthshine tends to be slightly brighter when the northern hemisphere is tilted toward the sun during northern winter, allowing the Moon to receive reflected light from snow-covered regions. Time of year also matters because Earth's reflectivity varies seasonally. During northern hemisphere summer, more of Earth's sunlight-receiving hemisphere consists of darker ocean, as the Pacific Ocean dominates the view from the Moon. During northern hemisphere winter, more land and ice face the Moon, increasing reflected light. These variations are subtle but measurable. Earthshine also changes with moon phase. It's most prominent during the waxing and waning crescent phases when Earth appears nearly full from the Moon. As the Moon approaches first quarter, Earthshine diminishes because Earth, as seen from the Moon, shrinks to half phase, reducing the amount of light reflected. At full moon, Earthshine effectively vanishes because the near side of the Moon is fully illuminated by direct sunlight, overwhelming the faint glow from Earthshine. And because Earth as seen from the Moon is at new phase, showing only its dark night side. Scientists have used Earthshine observations to study Earth's climate. By measuring how much light Earth reflects, quantifying our planet's bond albedo, researchers can track changes in cloud cover, ice extent, and vegetation patterns. Variations in Earthshine reveal variations in Earth's reflectivity, which connects to climate processes like cloud formation, ocean circulation, and ice sheet dynamics. This technique, sometimes called Earthshine climatology, turns the Moon into a distant mirror that shows us our own planet's brightness changes. The phenomenon also demonstrates the interconnectedness of the Earth-Moon system. These are not isolated objects, but gravitationally bound partners that exchange not just tidal forces and angular momentum, but light itself. The Moon illuminates our night. We illuminate its night. This reciprocal relationship has persisted for billions of years, though the intensity of Earthshine has changed over time as Earth's surface evolved. 4 billion years ago, when Earth's surface was mostly molten rock and the atmosphere very different, Earthshine would have had different characteristics. Once oceans formed and continents emerged, Earthshine changed again. When life developed and eventually colonized the land, changing the planet's albedo through vegetation, Earthshine shifted once more. Today's Earthshine carries information about our current Earth, our clouds, our oceans, our ice caps, our forests. An observer on the Moon could study this light and learn about our planet's surface properties and atmospheric conditions. In fact, we do exactly that by observing Earthshine from Earth, using the Moon as a tool to measure our own planet's reflectivity in a way that's difficult to achieve through other methods. Observing Earthshine requires clear skies and good timing. It's best seen during the crescent phases, shortly after sunset for the waxing crescent, or shortly before sunrise for the waning crescent. Binoculars or a small telescope enhance the view, though Earthshine is visible to the unaided eye under favorable conditions. The contrast between the bright crescent and the dim glow of the dark portion creates a striking visual effect, showing the full circle of the Moon with two different levels of illumination. Earthshine also reveals the three-dimensional nature of the Moon. When you see only a bright crescent against the black sky, the Moon can appear almost like a flat arc. But when Earthshine illuminates the entire disk, the spherical nature becomes obvious. You see a globe in space, not a flat shape, with one portion brightly lit by the sun and the other softly glowing from Earth's reflected light. This perception of depth and volume makes the moon feel more real as a world in its own right, rather than simply a light in the sky. The phenomenon has inspired poetry and art throughout human history. Before science explained Earthshine, many cultures developed stories about the faint glow on the dark moon. Some traditions saw it as a ghostly presence. Others interpreted it as spiritual significance. Now, we understand it as physics, reflection, albedo, geometry, but the knowledge doesn't diminish the wonder of seeing our own planet's light reflected back from another world. A reminder that we live in a system where light bounces between objects, carrying information about surfaces and atmospheres across hundreds of thousands of kilometers of space. Although the moon is tidally locked and always keeps the same face toward Earth, we don't see exactly the same 50% of the lunar surface all the time. Over the course of a month, the moon rocks back and forth and nods up and down in ways that reveal slightly more surface area along the edges of the disk. These apparent oscillations, called libration, allow us to see approximately 59% of the moon's total surface area over time, though never more than 50% at any single moment. Libration comes from the Latin word for balance, suggesting a swaying or tipping motion like a scale finding equilibrium. Three main types of libration affect the moon: libration in longitude, libration in latitude, and diurnal libration. Together, they create the gentle wobbling motion that reveals the extra 9% of the lunar surface. Libration in longitude results from the moon's elliptical orbit. The moon travels around Earth in an ellipse rather than a perfect circle, which means its distance from Earth varies throughout the month. When the moon is closer to Earth at perigee, it moves faster in its orbit according to Kepler's second law, which states that a line joining a planet and the Sun sweeps out equal areas in equal times. The same law applies to moons orbiting planets. The moon's orbital speed increases when it's closer to Earth and decreases when it's farther away. However, the moon's rotation rate remains constant. The moon rotates once every 27.32 days, regardless of where it sits in its elliptical orbit. This creates a mismatch between the moon's position in its orbit and its rotational orientation. When the moon moves faster than average in its orbit, its rotation can't keep up, so we see slightly around the leading edge. When the moon moves slower than average, its rotation gets slightly ahead, so we see slightly around the trailing edge. This back-and-forth rocking reveals about 8 degrees of extra longitude on the eastern and western limbs over the course of a month. Libration in latitude occurs because the moon's rotation axis is tilted about 6.7 degrees relative to the plane of its orbit around Earth. This is similar to how Earth's axis is tilted 23.5 degrees relative to its orbital plane around the Sun, creating our seasons. The moon's tilt means we sometimes see slightly over the North Pole and sometimes slightly under the South Pole, depending on where the moon is in its orbit. This nodding motion reveals about 7 degrees of extra latitude near the lunar poles. The combination of longitude and latitude libration creates a complex pattern where the moon appears to rock east-west while simultaneously nodding north-south. If you photographed the moon at the same phase over multiple months and compared the images carefully, you would notice that features near the limb shift position. Craters that appear right on the edge in one photograph might be slightly more visible or less visible in another taken weeks or months later. This movement is libration, revealing territory that would otherwise remain permanently hidden from Earth's view. Diurnal libration, the third type, results from observing the moon from different positions as Earth rotates. When the moon rises, you observe it from one position on Earth's surface. 6 hours later, when the moon reaches its highest point in the sky, you've been carried about 6,000 kilometers by Earth's rotation, giving you a slightly different viewing angle. This shift lets you see about 1 degree beyond the western limb when the moon rises and 1 degree beyond the eastern limb when the moon sets. Diurnal libration is small compared to the longitude and latitude libration, but it contributes to the total amount of lunar surface visible over time. There's also a fourth type, called physical libration, which is much smaller than the others. Physical libration represents actual small wobbles in the moon's rotation caused by gravitational torques from Earth acting on the moon's irregular mass distribution. These are real rotational variations, not just apparent effects from changing viewing geometry. Physical libration is less than 1 degree in magnitude and requires precise measurements to detect. When you add up all types of libration, they allow observers on Earth to see 59% of the moon's surface over time. The remaining 41% remains permanently hidden from direct observation. This hidden region is the far side, which was completely unknown until the Soviet Lunar 3 spacecraft photographed it in October 1959. The far side looks significantly different from the near side. It has fewer maria and more heavily cratered highland terrain, a difference related to the moon's center of mass being offset slightly toward Earth, which affects how the crust formed and how impacts distributed across the surface. Libration also means that there are small regions near the lunar limb where Earth occasionally dips below the horizon as seen from the moon. These areas experience what astronomers call libration zones, where Earth rises and sets over periods of weeks or months instead of remaining fixed in the sky. Most of the moon's near side sees Earth constantly hanging at essentially the same position in the lunar sky, never rising or setting. But in the libration zones, Earth's position varies, sometimes dipping out of sight below the horizon before returning to view as libration reverses. For observers interested in lunar topography, libration creates opportunities to see features from different angles. A crater located near the eastern limb might appear foreshortened and compressed when libration favors the western limb, then appear more face-on and circular when libration swings the other way. Lunar atlases and maps must account for libration when identifying features, noting that appearance varies depending on when you observe. Libration is gentle enough that casual observers don't notice it without careful attention or photographic comparison. The moon doesn't appear to shake or wobble when you watch it. The motion unfolds over days and weeks, too slowly for direct perception. But time-lapse photography makes it obvious. Several space agencies and amateur astronomers have created movies showing a month's worth of moon observations compressed into a few seconds, clearly revealing the rocking and nodding motion as libration carries the lunar disk through its cycle of apparent orientations. This wobble is one more reminder that the Earth-Moon system, despite appearing simple, contains subtle complexities. Tidal locking creates synchronous rotation, but elliptical orbits create speed variations that produce longitude libration. Axial tilt creates latitude libration. Earth's rotation creates diurnal libration. Mass irregularities create physical libration. The result is a moon that shows slightly different faces at different times, generous enough to reveal just over half its surface to patient observers willing to watch the sky over months and years, noting what features appear along the limbs and how their visibility changes with the moon's position and orientation. The moon does not orbit Earth in a perfect circle. Its path traces an ellipse, a squashed circle that brings the moon closer to Earth at one point in each orbit and farther away at the opposite point. When the moon reaches its closest approach, at a distance of approximately 356,500 kilometers, we call this point perigee. When the moon swings to its farthest distance, approximately 406,700 kilometers, we call this point apogee. The difference between these distances is about 50,000 kilometers, roughly 1.2 times Earth's circumference. This variation in distance affects the moon's apparent size in our sky. At perigee, the moon's angular diameter measures about 33.5 arc-minutes. At apogee, it measures about 29.5 arc-minutes. The ratio between these values means the full moon at perigee appears about 14% larger in diameter than the full moon at apogee, and therefore about 30% brighter, since brightness scales with the area of the illuminated disk. These differences are large enough to notice if you photograph the full moon at perigee and apogee and compare the images side by side, though casual observation rarely reveals the size difference because we have no reference points in the empty sky to judge the moon's diameter against. When a full moon coincides with perigee or near perigee, the media often calls it a supermoon. The term originated in astrology, not astronomy, but has been adopted by popular culture to describe full moons that appear larger and brighter than average. There's no official astronomical definition of supermoon, and different sources use slightly different criteria. Some define it as a full moon occurring within 90% of the closest approach distance. Others use different thresholds. Typically, a calendar year might have 3 or 4 supermoons, though the number varies. The opposite phenomenon, when full moon occurs near apogee, is sometimes called a micromoon, though this term has gained less public recognition. A micromoon appears 14% smaller and 30% dimmer than a supermoon, though again, the difference is difficult to perceive without direct comparison or measurement. The moon's elliptical orbit results from the gravitational interactions that shaped the Earth-Moon system. When the moon formed, gravitational perturbations from the sun and other effects prevented the orbit from circularizing completely. Even today, the sun's gravity continues to perturb the moon's orbit, creating the ellipse and causing its orientation to rotate slowly over time. The major axis of the ellipse, the line connecting perigee and apogee, rotates through 360 degrees over a period of 8.85 years. This means perigee doesn't always occur at the same point in the moon's orbit relative to the stars. The ellipse's orientation precesses, rotating gradually in the direction opposite to the moon's orbital motion. This precession creates a cycle called the anomalistic month, lasting 27.55455 days, which we mentioned earlier. This is the time between successive perigees, slightly longer than the 27.32-day sidereal month because the moon must travel slightly more than 360 degrees to return to perigee due to the precessing orbit. The variation in distance also affects the moon's orbital speed. When the moon approaches perigee, it moves faster, reaching speeds up to 3,716 kilometers per hour. When it swings out to apogee, it slows to about 3,630 kilometers per hour. This speed variation is what creates the libration in longitude that we discussed earlier, since the moon's rotation rate stays constant while its orbital speed changes. The elliptical orbit also influences tides on Earth, though less than the moon's phase does. Tides are strongest when the sun, Earth, and moon align at new or full moon, creating spring tides. Tides are weakest at quarter phases when the sun and moon pull at right angles, creating neapy tides. But the moon's distance adds another layer of variation. When perigee coincides with a new or full moon, creating a perigean spring tide, the tidal forces reach their maximum strength, sometimes raising tides 10 to 20 centimeters higher than average spring tides. When apogee coincides with quarter phases, creating apogean neap tides, tidal forces reach their minimum. These variations matter for coastal flooding and navigation in shallow waters. The moon's distance has changed dramatically over geological time. When the moon first formed, it orbited at approximately 20,000 kilometers from Earth, less than 6% of its current distance. At that range, the moon appeared enormous in Earth's sky, perhaps 15 times wider in angular diameter than it does now. The tides raised by the moon were correspondingly more powerful, possibly hundreds of meters high. Though Earth's surface was mostly molten at that time, so water oceans didn't exist yet to experience those tides. As the moon receded, both its apparent size and its tidal influence diminished. 4 billion years ago, the moon might have appeared 10 times wider than today. 3 billion years ago, perhaps 5 times. 1 billion years ago, perhaps twice as large. The moon reached its current distance range within the last few 100 million years and continues to drift outward at 3.78 centimeters per year, slowly but steadily increasing the perigee and apogee distances. This recession means that total solar eclipses, which occur when the moon's apparent diameter equals or exceeds the sun's apparent diameter, allowing the moon to completely cover the solar disk, will eventually cease. Currently, the sun and moon have nearly the same apparent size in our sky, a remarkable coincidence that allows both total solar eclipses, when the moon appears slightly larger than the sun, and annular solar eclipses, when the moon appears slightly smaller and leaves a ring of sunlight visible around its edges. As the moon recedes, total eclipses will become rarer, eventually, becoming impossible when the moon's maximum apparent size becomes smaller than the sun's minimum apparent size. This transition will occur in approximately 600 million years. After that, all solar eclipses will be annular or partial. The last total solar eclipse will occur, unwitnessed and unmarked, and then they will be gone forever. For now, we inhabit the epoch when total solar eclipses still occur, when the full moon can still grow large enough at perigee to cover the sun completely. We live in the brief window, geologically speaking, when our planet has both continents and oceans, complex life, intelligent observers, and a moon that happens to match the sun's apparent size closely enough to create total eclipses. This combination won't last forever, but it exists now, during our lifetimes, allowing those who chase eclipses to witness the full spectacle of totality. The elliptical orbit, the varying distance, the changing apparent size, all of these emerge from orbital mechanics and gravitational physics. Kepler's laws predict them. Newton's theory of gravity explains them. Einstein's general relativity refines the understanding with corrections for space-time curvature, though these corrections are tiny for the moon's orbit. The ellipse is not a flaw or imperfection, but a natural consequence of how gravity shapes motion in space, creating orbits that follow conic sections, ellipses, parabolas, or hyperbolas depending on the object's speed and energy. The moon's energy and speed place it on an elliptical path, bound to Earth but not constrained to a circle, forever swinging between closer and farther, faster and slower, larger and smaller in our sky. The moon formed in violence. Current scientific understanding points to a catastrophic collision between early Earth and another planetary body as the most likely origin of our satellite. This event, called the Giant Impact, or sometimes the Big Whack, occurred approximately 4.5 billion years ago during the final stages of planetary formation in the inner solar system. Understanding how the Moon formed helps explain its composition, its size relative to Earth, and why the Earth-Moon system has such unusual characteristics compared to other planet-satellite pairs in the solar system. The impacting body is called Theia, named after the Titan in Greek mythology, who was the mother of Selene, the moon goddess. Theia is thought to have been roughly the size of Mars, with a mass perhaps 10% that of Earth. It formed in the inner solar system and followed an orbit that eventually crossed paths with proto-Earth. The collision was not a head-on impact, but a glancing blow, with Theia striking Earth at an oblique angle. This angle is important because a direct head-on collision would have destroyed both bodies completely, while a perfectly tangential graze might have resulted in a different outcome altogether. The impact released energy equivalent to billions of nuclear weapons, instantly vaporizing portions of both Theia and Earth's outer layers. The collision ejected tremendous amounts of material into orbit around Earth. Mantle rock from both bodies superheated into vapor and liquid droplets. This debris cloud formed a ring around Earth similar to but far more massive than Saturn's rings. Over the following thousands of years, material in this debris disk gradually coalesced through gravitational attraction, building up into larger and larger chunks. Eventually, these chunks merged into a single molten body, the Moon. Evidence supporting the giant impact hypothesis comes from multiple sources. The Moon's composition resembles Earth's mantle more than its core, which makes sense if the Moon formed from material splashed off Earth's outer layers rather than forming independently. The Moon is depleted in volatile elements and compounds, substances that evaporate easily, which accords with formation from superheated material where volatiles would have escaped into space. Analysis of lunar samples returned by Apollo missions shows that Moon rocks have similar isotopic ratios to Earth rocks for many elements, suggesting they share a common origin, but also show differences consistent with high-temperature processing during formation. Computer simulations of the giant impact consistently produce results matching observed characteristics of the Earth-Moon system. When researchers model a Mars-sized body striking proto-Earth at angles between 30 and 45 degrees and speeds around 4 kilometers per second, the simulations generate a debris disk that subsequently forms a single large moon at approximately the right distance from Earth. The models also show that Earth's rotation period after the impact would have been about 5 hours, much faster than today's 24-hour rotation, which matches evidence from tidal evolution showing that Earth has been slowing down due to the Moon's tidal forces. The giant impact also explains why the Earth-Moon system has relatively high angular momentum compared to other planet-satellite pairs. Angular momentum is the measure of rotational motion, and the Earth-Moon system possesses more of it than would be expected if the Moon formed from a slowly accumulating disk of material or if it was a separate body captured by Earth's gravity. The violent off-center collision added rotational energy to the system, spinning up both Earth and the newly forming Moon. Alternative theories for the Moon's origin have been largely abandoned because they fail to explain the observations as well as the giant impact does. The co-formation theory, which proposed that Earth and Moon formed together from the same cloud of material, cannot explain why the Moon lacks a large iron core like Earth has. The capture theory, suggesting the Moon formed elsewhere and was later captured by Earth's gravity, requires implausibly specific circumstances to result in the Moon's current orbit and doesn't explain the isotopic similarities between Earth and Moon rocks. The fission theory, proposing that the Moon split off from a rapidly rotating Earth, cannot account for the angular momentum distribution and has other physical problems. The giant impact hypothesis isn't without questions. One puzzle is why the Moon's composition is so similar to Earth's if it formed partly from Theia, which presumably had a different composition since it formed in a different part of the solar system. Some researchers suggest that the impact and subsequent mixing of vaporized rock created such thorough blending that the final Moon inherited primarily Earth-like composition with only traces of Theia's contribution. Others propose that Theia happened to have composition very similar to Earth, perhaps because it formed at a similar distance from the Sun. Recent simulations exploring different impact scenarios have found configurations that produce better mixing and explain the isotopic similarities more naturally. Another question concerns the Moon's current orbit, which is inclined about 5 degrees to Earth's equatorial plane. The debris disk that formed the Moon should have been aligned with Earth's equator, so the Moon should have formed in an equatorial orbit. The current inclination suggests something perturbed the Moon's orbit after formation. Gravitational interactions with remnant debris, resonances with the Sun's gravitational influence, or other effects during the early solar system's chaotic phase may have tilted the orbit to its present configuration. The timing of the giant impact remains somewhat uncertain. The most precise age estimates come from radiometric dating of lunar samples. The oldest lunar rocks found by Apollo missions date to about 4.4 billion years, and most lunar formation models place the impact around 4.5 billion years ago, within the first 100 million years of the solar system's existence. This timing fits within the broader context of planetary formation, when frequent large collisions cleared the inner solar system of planet-sized bodies and established the current architecture of Mercury, Venus, Earth, and Mars. After the Moon coalesced from the debris disk, it was initially much closer to Earth than it is today, orbiting at perhaps 15,000 to 20,000 kilometers altitude. At this proximity, it would have appeared gigantic in Earth's sky, subtending perhaps 10 to 15 degrees of arc compared to the half-degree it shows now. The tidal forces at such close range were immense, raising enormous bulges in Earth's still molten mantle and generating tremendous heating from tidal friction. This heating, combined with the heat of formation, kept the Moon molten for millions of years. Eventually, the surface cooled and solidified, forming the anorthosite crust that makes up the bright lunar highlands we see today. The darker Maria formed later, between about 3.8 and 3 billion years ago, during the late heavy bombardment when increased impact activity throughout the inner solar system sent waves of asteroids and comets crashing into planetary surfaces. Large impacts on the Moon punch through the crust, allowing basaltic lava from the mantle to flood the impact basins. This lava is darker than the anorthosite crust, creating the contrast between bright highlands and dark Maria that gives the Moon its familiar pattern. The near side has more Maria than the far side, a difference related to the Moon's slightly offset center of mass and the resulting variation in crustal thickness between hemispheres. By 3 billion years ago, the lunar surface had essentially reached its modern appearance. Later impacts added craters like Tycho, Copernicus, and Kepler with their bright ray systems, but the major mare basins had formed and filled. The Moon settled into the relatively quiet existence it maintains today, cratered by occasional impacts but no longer geologically active, tidally locked to Earth and slowly receding, the product of an ancient violence that created perhaps the most significant partnership in the solar system, a large planet with a large satellite sharing their journey around the Sun. The term blue moon has entered common language to describe rare events, as in the phrase, once in a blue moon. But what actually constitutes a blue moon in astronomical terms has changed over time and depends on which definition you follow. Currently, the most widely accepted definition describes a blue moon as the second full moon occurring within a single calendar month. Since the synodic month lasts 29.53 days and most calendar months contain 30 or 31 days, most months contain only one full moon. But occasionally, timing aligns such that two full moons fit within the same month, making the second one a blue moon by this definition. This situation occurs approximately every 2.5 to 3 years. For two full moons to fit in one month, the first must occur on the first or second day of the month, allowing the 29.5-day cycle to complete before the month ends. The exact frequency varies because calendar months have different lengths and because the synodic month varies slightly in duration. On average, blue moons by this definition occur about 7 times every 19 years, though the distribution isn't perfectly regular. Interestingly, this modern definition of blue moon originated from a misinterpretation. The older, original definition classified a blue moon as the third full moon, in a season that contains 4 full moons instead of the usual 3. Seasons, as marked by solstices and equinoxes, typically contain 3 full moons. When a season contains 4, the third one was traditionally called a blue moon. This definition is more complex and less intuitive than the simpler calendar month rule, which may explain why the newer definition gained wider acceptance after being popularized in the mid-20th century. Neither definition refers to the moon actually appearing blue in color. The moon does not turn blue during a blue moon as defined by calendar criteria. However, the moon can occasionally appear blue due to atmospheric effects, though this has nothing to do with the calendar-based blue moon phenomenon. When volcanic eruptions inject large quantities of ash and sulfur dioxide into the upper atmosphere, these particles can scatter red light preferentially while allowing blue light to pass through. This can temporarily give the moon a genuinely bluish appearance. The eruption of Krakatoa in 1883 produced blue moons visible worldwide for nearly 2 years. The Canadian forest fires of 1951 created similar effects. These events are rare and unpredictable, unrelated to the orbital timing that produces calendrical blue moons. Another lunar phenomenon worth mentioning is the black moon, a term much less well known than blue moon but parallel in concept. A black moon most commonly refers to the second new moon occurring within a single calendar month, making it a counterpart to the 2 full moons blue moon definition. Since new moons are invisible, black moons pass completely unnoticed, except by those tracking the lunar calendar specifically. The term also sometimes describes a month with no new moon at all, which can occur in February during certain years, since February has only 28 or 29 days, while the synodic month lasts 29.53 days. The infrequency of these phenomena has given rise to the expression once in a blue moon, meaning rarely or hardly ever. The phrase dates back at least to the 16th century in English, though its specific connection to the astronomical phenomenon became standardized more recently. The expression captures the sense of temporal rarity and has proven useful enough to persist in language even as many speakers remain unaware of the astronomical context. Beyond blue moons, other rare alignments and phenomena occasionally occur. One is the supermoon, already discussed, when full moon coincides with perigee. Another is a blood moon, a popular term for the reddish appearance the moon takes during a total lunar eclipse. During totality, Earth's atmosphere refracts sunlight around our planet. bending red wavelengths into Earth's shadow where the moon sits. This gives the eclipsed moon a coppery or blood-red color rather than making it completely dark. The term blood moon has ancient origins and appears in various cultural traditions and religious texts. A micromoon represents the opposite of a supermoon, full moon at or near apogee, when the moon appears at its smallest and dimmest. These occur with the same frequency as supermoons several times per year, but receive far less public attention because a smaller, dimmer full moon is less spectacular than a larger, brighter one. Very rarely, on the scale of centuries, multiple significant astronomical events can coincide. A blue supermoon, the second full moon in a month occurring at perigee, happened on August 31st, 2023. These coincidences require 3 independent cycles to align: the synodic month, the calendar month structure, and the anomalistic month. The rarity of such alignments adds to their appeal for skywatchers and media coverage, though the moon itself doesn't know or care about human calendar conventions and simply continues following the gravitational forces that govern its motion. Lunar phenomena also include transient events like impacts. Though rare on human timescales, meteors do occasionally strike the moon's surface with enough energy to create visible flashes of light. Amateur astronomers monitoring the moon during meteor showers sometimes detect these impact flashes, which appear as brief, bright spots lasting a fraction of a second. The moon has no atmosphere to burn up incoming objects, so even small meteoroids reach the surface at cosmic velocities, creating explosions that release visible light. NASA's Meteoroid Environment Office maintains a catalog of confirmed lunar impact flashes, which number in the hundreds since systematic observations began. These various phenomena, blue moons by calendar coincidence, rare color changes from atmospheric effects, eclipses, conjunctions with planets, impact events, add variety to lunar observation. While the basic cycle of phases repeats month after month with reliable consistency, these special events provide occasional deviations from the pattern, moments when the moon does something unexpected or when multiple cycles coincidentally align. They remind us that while celestial mechanics is deterministic and predictable, the richness of possible configurations means that interesting and unusual situations arise, with sufficient patience and attention to timing. For casual observers, most of these phenomena are indistinguishable from ordinary full moons or other phases except in knowing that a particular coincidence has occurred. A blue moon looks identical to any other full moon. Its significance lies in the timing, the calendar coincidence, rather than in any visual difference. Similarly, a supermoon appears only slightly larger than an average full moon, a difference most people cannot detect without direct comparison. The importance is often more cultural and psychological than strictly observational. We enjoy marking these events, noting when rare alignments occur, celebrating the intersections of different cycles. The moon provides a stable background against which we can track these patterns, a celestial clock whose multiple periods create intricate temporal harmonics that occasionally produce special moments worth noting and remembering. The moon's phases represent something fundamental about our position in the solar system. We orbit a star that provides light. Our planet has a satellite large enough to show a disk rather than appearing as a mere point. That satellite orbits close enough and slowly enough that its changing geometry relative to the Sun creates obvious phases visible to the unaided eye. This configuration is not unique in the universe, but it's relatively uncommon, and it has profoundly influenced how humans understand their place in space. Early observers of the sky didn't know about orbits or gravitation or the speed of light. They simply saw the moon changing shape and noted the pattern. From those observations, ancient astronomers built calendars, tracked seasons, predicted eclipses, and began to understand that celestial motions follow regular patterns. The moon served as humanity's first lesson in the predictability of the cosmos, demonstrating that the sky follows rules rather than divine whim. The phases teach us about geometry. When you understand why crescents and gibbous moons occur, you've learned that appearance depends on viewing angle. You've grasped that three-dimensional relationships between objects determine what we see in two dimensions. This insight extends beyond astronomy to any situation where perspective matters, where position affects perception, where seeing something from multiple viewpoints reveals aspects invisible from a single vantage point. The phases also teach us about cycles. Nature contains countless examples of repeating patterns: day and night, seasons, tides, heartbeats, planetary orbits. The lunar month is one of the most accessible cycles to observe, requiring no instruments, no mathematics, just attention to the sky over several weeks. Children can notice it. Ancient peoples noticed it. The cycle is obvious yet profound, a window into understanding that the universe operates through repeating processes, that what goes around comes around, that endings lead to new beginnings. The moon's distance, its recession, its formation, its tidal locking, all of these aspects reveal physics at work. The moon is not arbitrary. Its current state emerges from 4.5 billion years of gravitational interactions, energy dissipation, and orbital evolution. Understanding the moon means understanding how gravity shapes motion, how energy transfers between objects, how systems evolve toward equilibrium states. The moon is a laboratory for celestial mechanics, close enough to study in detail, simple enough to model with Newtonian physics, complex enough to demonstrate orbital perturbations and three-body effects. The fact that we can predict the moon's position and phase years or centuries in advance demonstrates the power of scientific understanding. We know where the moon will be in its orbit on any future date. We can calculate what phase it will show. We can predict eclipses decades ahead. This predictive capability comes from mathematical models of gravity and motion, refined over centuries of observation and calculation. It represents a triumph of human reasoning, the ability to compress patterns into equations and extend those equations forward and backward in time. Yet the moon remains mysterious in certain ways. Its exact formation scenario still generates debate among planetary scientists. The details of how its orbit evolved over billions of years contain uncertainties. The far side was completely unknown until spacecraft photographed it. The interior structure is still being refined through seismic data and gravitational measurements. Science doesn't claim perfect knowledge, just progressive understanding, models that improve as new data arrives and computational tools advance. The moon also connects us to our ancestors. Every human who has ever lived saw the same moon we see now, displaying the same phases in the same sequence. The moon witnessed all of human history and prehistory, shining down on hunter-gatherers, agricultural societies, industrial civilizations. It illuminated the paths of migrating humans spreading across continents. It lit the nights of ancient cities now long vanished. It inspired myths, religions, art, poetry, science. The moon is a shared experience across all cultures and times, one of the few constants in an ever-changing world. When you look at the moon tonight, you participate in an observation that humans have made for hundreds of thousands of years. The specific pattern of light and shadow you see depends on precise geometry, the angle between sun, earth, and moon, that will never be exactly replicated because the moon gradually recedes and Earth's rotation gradually slows. Every configuration is unique in the strict sense, though similar patterns repeat month after month. You see a particular moon at a particular moment, a configuration that emerges from the interplay of orbital periods and gravitational forces, visible because you happen to exist in this epoch when the moon orbits at this distance and shows this apparent size. The reliability of the phases provides comfort. In a complex, often unpredictable world, the moon follows simple rules. You can count on it. The phases will cycle. The moon will rise and set. The patterns will continue as long as the Earth-Moon system persists. This reliability makes the moon feel like a friend, a familiar presence in an otherwise vast and impersonal universe. It's close enough to seem approachable, regular enough to seem dependable, beautiful enough to inspire wonder. The next time you notice a crescent moon in the twilight or a full moon rising over the horizon, you might pause to consider the system that produces it. The sun 93 million miles away pouring light across the solar system. Earth spinning beneath your feet, carrying you around once every 24 hours. The moon moving in its elliptical orbit, traveling 13 degrees eastward each day, locked in. Synchronous rotation, raised by ancient impact, evolving through tidal forces, slowly spiraling away. All of these elements create the simple appearance of a shape in the sky, a shape that changes night by night according to the geometry of the system. Understanding doesn't diminish the beauty. If anything, it enriches observation by adding layers of meaning. The crescent becomes not just a pretty shape, but evidence of the moon's position between Earth and Sun. The timing of moonrise becomes a clue to phase and orbital position. The brightness variations connect to distance changes and albedo. The dark portion glowing with Earthshine shows light's journey from Sun to Earth to Moon and back. Every aspect of the moon's appearance tells you something about the system if you know how to read it. And yet the moon remains accessible to those who don't know or care about the physics. It offers beauty without requiring understanding. A child can appreciate a full moon without knowing about illumination, geometry. A poet can find inspiration in a crescent without understanding orbital mechanics. The moon serves many purposes, fills many roles. It's a scientific object, a cultural symbol, an aesthetic experience, a navigational tool, a calendar reference, a source of tides, a gravitational partner. It exists in physical space following mathematical laws, but it also exists in human experience and imagination, evoking emotions and associations that transcend mere measurement and prediction. This dual nature, objective and subjective, physical and meaningful, characterizes much of human relationship with the natural world. We study nature scientifically while also experiencing it aesthetically and emotionally. The moon exemplifies this duality perfectly. Its rocks and craters governed by gravity and orbital mechanics. It's also the harvest moon, the hunter's moon, the wolf moon, the moon of poetry and songs and myths. Both aspects are real. Both aspects matter. Science tells us how the moon works. Culture tells us what it means. Together, they create a fuller understanding than either could alone. The moon continues its journey around Earth, month after month, year after year, following the path established billions of years ago when debris from an ancient impact coalesced into the satellite we see today. The phases will keep cycling through their sequence: new moon, waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, waning crescent, and back to new. This pattern has repeated roughly 54 billion times since the Moon formed, and it will continue for billions more before the Sun's evolution disrupts the system. Each phase results from the same simple geometry. The Moon orbiting Earth while both orbit the Sun, with sunlight illuminating half the Moon, and our viewpoint determining how much of that illuminated half we see. The waxing phases show more illumination night by night as the Moon swings from between Earth and Sun toward the opposite side of Earth. The waning phases show less as the Moon returns toward its starting position. The cycle takes 29.5 days to complete, a period that human cultures have recognized and tracked for millennia. The Moon doesn't hurry. Its changes unfold gradually, too slowly to perceive in real time, but obvious over hours and days. This gentle pacing makes the Moon perfect for long observation sessions, for returning to the sky night after night to watch the progression, for noticing details you missed previously. The Moon rewards patient attention with subtle revelations: earthshine during crescents, libration-shifting features along the limbs, color variations in different atmospheric conditions, the changing timing of moonrise and moonset. Understanding the Moon's phases connects you to the geometry of the solar system. You begin to visualize the three-dimensional arrangement of Sun, Earth, and Moon based on what phase you observe. A waxing gibbous tells you the Moon is approaching full, lying almost opposite the Sun from Earth. A waning crescent tells you the Moon is swinging around between Earth and Sun, approaching new phase. The sky becomes a diagram you can read, translating shapes and positions into spatial relationships. This knowledge doesn't require advanced mathematics or specialized equipment. It emerges from observation and thought, from paying attention to patterns and asking why they occur. Ancient astronomers figured out much of this without modern physics, working from careful records and geometric reasoning. The Moon makes excellent teaching material because it changes obviously over accessible timescales and responds to simple geometry rather than requiring complex calculations. The Moon will rise tonight somewhere on Earth, perhaps as a thin crescent in the evening sky, perhaps as a gibbous disk climbing above the eastern horizon hours after sunset. Wherever it appears, it will show some phase of its monthly cycle, displaying the illuminated portion created by sunlight and geometry. Someone will notice it and perhaps wonder why it looks that way. Someone else will recognize the phase and know approximately where the Moon sits in its orbit. Someone might photograph it or sketch it or simply appreciate its beauty without analysis. All of these responses are valid. The Moon exists for scientific study, but it also exists as a presence in the night sky, a source of light and wonder that requires no justification beyond its own existence. It's been there all along, orbiting Earth, displaying its phases, waiting patiently for anyone who looks up to notice it and perhaps understand a bit more about how our local corner of the universe operates. If you found this exploration helpful or interesting, if it gave you a different perspective on the Moon, or helped you understand why the phases occur, then perhaps consider subscribing to Nebula Nights. We explore astronomical topics in this same calm, detailed style, aiming for understanding rather than urgency, for depth rather than brevity. The universe contains countless fascinating phenomena worth examining carefully and thoughtfully, and the Moon is just the beginning. There are planets to explore, stars to understand, galaxies to contemplate, all following physical laws that we can comprehend through patient study and clear explanation. A like on this video helps it reach other people who might be curious about the Moon's phases or who enjoy learning about space while relaxing or falling asleep. Subscribing ensures you'll see future videos on similar topics. And if you have questions about the moon or suggestions for other subjects you'd like to see covered in this format, the comments are open. Thank you for spending this time exploring the moon's phases. Whether you listened straight through or dipped in and out, whether you absorbed every detail or let the information wash over you. As you drifted towards sleep, the moon continues its orbit regardless, following the same path it has traced for billions of years, displaying the same phases in the same sequence, governed by the same gravitational forces. It will still be there tomorrow night and the night after, gradually changing from whatever phase you see now toward the next phase in the cycle, reliable and constant and beautiful in its motion through the sky. Clear skies.